Hello, physics fans. Today we get a special two-part lecture. The first part will be quite short, be about 5-10 minutes, and then you'll have the main part of the lecture. We're going to do a demo today, which is why you've got me up close instead of down at the bottom of the room, videotaping from the top of the room. Today we're going to be doing a demo that shows one of the applications of magnetic induction, and then we'll explain what magnetic induction is and why it created the series of events that you saw. So here we have our setup. This is an induction cooker. You can buy one of these on eBay for about 50 to 60 bucks usually. This is a little bit higher end model, so it was about 100 bucks. And you see four things. You see an ice cube, which is slowly melting because it's rather warm in this room, which is weird considering it's December, at least when I'm videotaping this. You see a jar of peanut butter, and you do see a brand name, so you know that it's peanut butter. This company does not endorse my lecture. Okay. It looks like product placement, but it's not. And a thing of chili. Now, what we're going to do is we're going to turn on the oven and see what happens to these objects, as well as the small pot of water that we're going to attempt to boil. Now, usually at home it takes about 10 minutes to boil water. So we're going to turn this on. And this is a pretty high power, 1400 watts. And we're going to see how long it takes to boil the water, as well as what happens to the other stuff. Now, I should at this point tell you to not do this at home. I am not an expert. I'm not a professional. An expert, but not a professional. So this could get messy. In fact, I should back up some. Because we all know what happens to cans of stuff when you heat them too much. Boom! And I'd rather not get maimed and injured by flying projectiles. Well, so far the ice is not melted, so it looks like it's going to take a little while to heat up. That tends to happen even on your conventional stovetop. Now, a conventional stovetop works by doing the following. It runs an electric current through a giant resistor. That resistor heats up to several thousand degrees, and it takes a while to do that. And then that resistor, when you put the pan on it, heats the pan, which then heats the water. So it's a bit indirect because the pan is the middleman, and every time you have a middleman, well, there's inefficiencies. And so it's only about 40% efficient. That means 40% of the energy you actually consume using the stove actually goes to heating the water. The other 60% just heats your house. In this case, we're a bit more direct. We actually generate a current, how I'll talk about later, directly in the pan, and so the pan is heated directly. And then that heated pan then heats the water. It is twice as efficient, which allows us to boil the water twice as quickly. And you can see from this that we're about 3 minutes into this talk, of which I spent probably the first 2 minutes not having the thing on. And you can see already it is starting to bubble. Now, I wouldn't call that a complete boil yet, but if I stick my finger in there, it is very warm. You would not want to bathe in that. That would hurt. Well, the ice cube is not melting yet. Interesting. The can has not just been destroyed yet, but our water's not going in. My peanut butter in a plastic jar does not seem to be melting yet. So maybe I won't get Peter Pan all over the place. Okay. Well, the water continues to bubble a bit, and you can see it's starting to steam. I don't know if you can quite make that out in the video. It is starting to steam a little bit, but I wouldn't call it a full boil. But it's definitely getting there. If I was cooking pasta, I'd be putting the pasta in right about now. And it usually takes about 10 minutes on a conventional stove to get to this point. Now, a little hand waving because I do have a small pan, and therefore there's a small amount of water, and so it's a little bit easier to boil. If I had a bigger pan, it would definitely take longer. But you can see this is happening very, very quickly. And in fact, I really don't have much time to do anything but comment on what's happening. No lulls here. And it is almost completely boiling now. You can see it is almost a complete boil. It is pretty darn close. My ice cube is still, well, it's melting a little bit because you have room temperature and the pan is heating the glass, which then melts the ice cube a little bit. And the bottom of my heater pan is okay. I'll move it a little bit closer. My beans, are actually quite warm. Okay. I guess I grabbed a can that was ferromagnetic. Okay. Oops. So I guess magnets would stick to that. So we'll take that off. I guess I'll be eating that for dinner tonight. I can actually hear it gurgling, so I definitely did a good job of heating it. Definitely don't want to do anything more with that. Okay. Because that would, what would happen is the top would probably blast off at some point. Probably very violently. So I want to move that as far away from me as possible. Usually if you have a normal tin can, the bottom gets a little bit warm, but the entire can usually does not get warm. I guess this can is made of iron and not tin. So that meant a bit of a fail in my experiment there, but these things happen. All right, I would call that a boil, and it's only been a few minutes, maybe 4 or 5 minutes, and you can see it's a complete boil. Now, on your stove at home, if you turned off the stove, it would continue to boil for several minutes more because it takes a while for that coil to decrease its heat, and so it's continuing to heat the pan, which continues to heat the water. Now, let's observe what happens when I turn off this. And remember, there is no CGI, no video graphics here, no editing, because I don't know how to do any of that. So let's turn it off. And it stops boiling immediately. Because there's no longer heat generated to the pan, which means there's no longer heat being distributed to the water. And so it just remains its current temperature. And by the way, it takes a lot of energy to go from heated water to boiled water. It's about 3 times more than what it takes to actually heat the water up in the first place. But my ice cube's still nice. My Peter pan is still unchanged. And the only reason I had to remove my can of chili was because I didn't realize that that can was ferromagnetic. Usually cans are not. So if you do this experiment at home, make sure your can doesn't stick to magnets. Oops. So what happened here? Why did the peanut butter not do anything? Why did the ice cube not do anything, but the water boiled rather rapidly? Well, this is called an induction cooker. And what it does is it fluctuates a magnetic field. And as we're going to learn in just a moment, a fluctuating magnetic field induces a current. Now, to induce a current, you have to be able to move a charge. If you can't move the charge, you can't generate a current. This is an insulator. It doesn't move charges very well. There's no current. This doesn't have any ferromagnetic metal. It's water. It doesn't generate a current. Now, I'm about to do something that this device tells you not to do. I have it upside down. And it says, notice crystallite glass is hot after cooking. Please don't touch with your hand. This is a safety warning to prevent people from doing what I am about to do. So definitely do not do this at home, because I've done this a time or two. It is very hot. But that's because the pan has heated the glass. But still, I could touch it in a few minutes. It'll cool off very quickly, and it'll be fine. In fact, I could probably put my ice cube over that and speed up that process. That's one way to get my ice cube to finally melt. So, if I put my hand here, even if I had it turned on, my hand would do nothing because I don't have any metals in my hand that magnet will stick to. At least not very much of it. A little bit of iron in the blood, but it really won't heat up my hand. That's why the peanut butter didn't heat up. That's why the ice cube really didn't heat up. But the but the water did because this pan will stick to metals. It's ferromagnetic. Aluminum pans, by the way, won't work on an induction cooker, but cast iron works great. So this is an induction cooker. It's twice as efficient, twice as fast as your traditional stovetop, and gives you a lot more control over what you're cooking. I actually use induction cookers at home myself. I have 3 of them. One is a backup. I got cheap at an auction. And then I have 2 others that I bought off of eBay, one to cook my meat and one to cook my pasta. So I use them. They're great, and they use the concept of magnetic induction. So now we're going to take a pause here and go to part 2. So in a moment, I'll be at part 2. See you in a bit.